Hello students and welcome to chemistry at JP's Academy, and I am Nitin sir. Students, in this session of the chapter Gaseous State, we are going to do a very important topic, which is Dalton's law of partial pressure. So before I start the session, I want everyone to quickly like, subscribe and please share this video. So students, what exactly is Dalton's law of partial pressure? Students, let's consider that I have three identical containers. They have the same volume and they are at the same temperature. In the first container, I have gas A. We can consider, let's say, gas oxygen, which is at a pressure PA or PO2. In the second container, I have a gas B, which is, let's say, at pressure PB. For some example, we can also take, let's say we have nitrogen over here. Now students, if I mix the two gases, and in the third container now I have both the gases, gas A and gas B, then Dalton's law of partial pressure says that if I have a mixture of non-reactive gases, then the total pressure of the non-reactive gaseous mixture will be equal to the sum of their individual partial pressures. So the total pressure students over here in this container will be partial pressure of the first gas and partial pressure of the second gas. Please remember, these should be non-reactive gases. Now students, let me quickly write that for you. So Dalton's law of partial pressure says that the total pressure of a mixture of non-reactive gases is the sum of individual partial pressures of the gas. Now students, we can also prove this. So if we apply, students, the ideal gas law to the first container, let's say that students, in the first container we have Na number of moles of gas A. Then we know that students, according to ideal gas law, PV is equal to nRT. The pressure over here is PA, volume of the container is V, the number of moles of the container is Na into R into T. Similarly students, let's say that in the container B, the number of moles of gas B is B. So we can now write PV into V is equal to NB into RT. And over here students, since we have mixed both the gases and these are non-reactive gases, the total number of moles will become Na plus Nb, and I can write the equation for Pt over here as Pt into V is Na plus Nb times RT. Now students, I mark this as equation number 1 and this as equation number 2 and this as equation number 3. Now students, if I take the sum of equation 1 and equation 2, so I get the equation as PAV plus PBV is equal to NART plus NBRT. Over here students, what we observe is that V is constant. So I get bracket में PA plus PB into V is equal to NA plus NB times RT. I can see RT is common over here. And students, from here When I look at equation number 3, I observe that the RHS over here are equal. And then I can say that PA plus PB times V is equal to PT times V. And since the volume of the containers are equal, we get the expression PA plus PB is equal to PT. Next, students, we can also write one more expression over here. So, we know that, students, PA into V is NA times RT. And we know that PT times V is NA plus NV times RT. If I divide the two equations, I repeat, if I simply divide the two equations, what I observe here is, since the volume of the container is same and the container at the same temperature and R is universal gas constant, PA over PT is equal to NA over NA plus NB. And students, number of moles of a component to the total number of moles is given by mole fraction. So mole fraction of component A or gas A can be written as number of moles of A over number of moles of A plus number of moles of B, and so I get the expression as PA over PT is equal to mole fraction of A, or partial pressure of gas A in the container is mole fraction of gas A into total pressure. Or students, we can write the expression as the partial pressure of any gas in a non-reactive mixture. The partial pressure of gas in a non-reactive mixture will be the mole fraction of gas. I repeat, will be the mole fraction of gas times total pressure. Total pressure. Similarly, since we had gas B, I can write partial pressure of gas B will be mole fraction of gas B into PT. And one more expression, students, always remember, I can write XB, mole fraction of gas B, as NB upon Na plus Nb, and the sum of mole fractions is always equal to 1. So students, this is another expression that we have derived from Dalton's law. Now students, what are the applications of Dalton's law? Now, in majority of experiments, what we observe is that gases are usually collected by downward displacement of water. So for example, over here you can see that, let's say I want to collect ammonia. So that is done by downward displacement of water. We see that the gas will come here and will get collected over here. But it's not that only gas gets collected, because the observed pressure here, I repeat students, the observed pressure of the gas over here will be the sum of the partial pressure of the gas over there and aqueous tension. And hence, whenever in an experiment we're doing downward displacement, we're collecting gas by downward displacement of water, what we have to be really careful is that the observed pressure of the gas, it will be moist gas, will be the partial pressure of the dry gas plus aqueous tension. And from here, students, we can find that the partial pressure of the dry gas will be the observed pressure minus aqueous tension. Very important for numericals in JEE and NEET. So students, this was a very small session on Dalton's law. If you need detailed numericals for the same, please let us know, because numericals on Dalton's law is very important. See you students in the next session, where we will discuss Graham's law of diffusion. Thank you so much.